Okay, so tonight we're going to be talking about chapter 4, network protocols and routing. Okay, and as you guys go through the book this week, the book we're going to definitely talk about TCP and IP. Remember, those are two separate protocols, and as you read the chapter this week, you're going to see that it's going to break them down separately. Okay, so identify how these different protocols work, format explain how routers, how to manage that, and employ various TCP IP utilities for network discovery and troubleshooting. And troubleshooting is always the best part. When you guys read these books, definitely always pay close attention to the troubleshooting section because that is really at the end of each chapter because that is really what's going to help you fix problems very quick and simple, and you won't be banging your head to the wall. Now, as I said at the beginning of the semester, this book gets very, very deep and it gets very, very granular. So we're going to hit the high surfaces because unless you guys plan to be network administrators or go deep, deep into this, some of this stuff you're not really going to need. So TCP and IP are two different core protocols. They call it a suite. Um, and it also includes UDP and ARC as well. So in the TCP/IP protocol, what it does, it adds a header to the application. When you get the browser one on the application layer, and then it just goes on down to the presentation layer, establishes a session, and then you can see from here the different things it's going to be doing, the payload, and from that as well. Let me just see if I can make this just larger. So just in case you can see the small print, that's a little bit better. Okay. So, and then it goes all the way down there. Once it gets to the physical layer, to the network, to the wiring and the physical piece, it sends all that information across through the network to the other computer or to the website or wherever it's trying to go. Then it puts it back in order and then it sends it back until you get to until it gets to its final destination. Okay. So on the OSI model, these are the different layers that it works at. So on layer 7, 6, and 5, data or instruction is known as the payload. That's where that is generated. Transportation, it transports at layer 4, and then it goes down to level 3. You remember we start from top to bottom. Level 3, the network layer asks, oh, this is where it asks a header and it breaks it down into the packets as it's getting ready to transmit that data. The layer 2 is going to the data link. It's talking to the NIC card. Now you're talking to your network card that's on your computer, and then once it does the encapsulations and put the trailer and the header and everything, it breaks it down. It's going to send it through the physical NIC card to the through the wire through the frame as well. Okay, so a little bit smaller there. Okay, so receiving holds the receiver host de-encapsulates the message at each layer in reverse order and present the payload to the receiving application. So it comes across one way. It comes across one way here. You can see it on the side here. It gets that same information and it de-encapsulates and it puts it back together and it sends it back the other way. That's what it's referring to right here. Uh, Connectivity devices are specialized devices that allow two or more networks or multiple parts of a network to connect to and exchange data. And it's talking about these different type of devices here on the side here: switches, routers, and firewalls. These are different type of connectivity devices which allow information to process. Known by the highest OSI layer is the read and write process. I'm not sure what that's. Probably jumped out of order there. Okay, so the TCP/IP operates on the transport layer of the OSI model. It's very important. You may see that on the quiz. Just keep that in mind. Okay, these are some of the main characteristics of the TCP/IP protocol. It's the connection-oriented protocols, which ensures that the connection or a session is established. So and it does this in 3 ways. It starts out a handshake, waits for acknowledgement from the handshake, and it sends out that sequencing and checksum. With TCP/IP sends a character string called a checksum that checks the destination host along the sequence number from each segment. And then it goes with flow control, gauges rates of transmission based on how quickly receiving can accept the data. So we want to know how fast can you talk? Is it quick here? So this slide here kind of goes into the segment and how it breaks it down. We're just gonna kind of pass over the slide because it's a little more deeper than what you guys really need. But looking at the three-way handshake here, it sends out the request. Okay, then it waits for a respond back, and then once you get the acknowledgement, it establishes a connection. You go ahead and establish that connection. After 3 attempts, then it go ahead and send the data. So it's going to try that 3 times, and it's pretty good. Our networks now are pretty solid. They're pretty reliable, and so usually for the most part, it's gonna work the first time around. Okay, so sequence numbers can be increased by the number of bits included in each segment that it receives. So that's just something that you should know. So basically, this is demonstrating the three-way handshake. Computer A is sending out to computer B. Is waiting for computer B to give an acknowledgement. It sends the information here. It sends it back. So that's right. So that's what I guess the acknowledgement is. So it sends it back here. And so this is just kind of what it works, but it's happening before the blink of an eye. And you think how fast this is happening because you guys never even notice it, and we're talking about you click on something and 30 seconds later, you're at the website. Not even 30 seconds, 5 seconds or 4 seconds, yahoo.com, you hit enter, you blink your eyes and the page is loading. So that's just how fast this data is transmitting. That's why, sometimes you just know it in theory, but you don't really have to know the steps by steps because you never see it. A UDP, a user datagram protocol, it's unreliable, it's connectionless protocol. No three-way handshake is performed, and it does not guarantee the data delivery. So, this is usually for like file transport, when you sending file from one computer to another, more in the technical sense, more on the commercial users. I don't really think they use as much, but like, say if you're working on, say a system or a computer and you're trying to fix it, like more like on the, for the lack of better words, I would say like programming it or something like that. You're trying to reload software, you got to transfer a file. That's when you probably use some type of UDP type protocol. UDP provides no error checking, seasoning, or flow control. Makes UDP more efficient than TCP/IP. That's because it's faster. They're basically what they're saying here is that because it's not checking for errors and it's not going back and forth. Look, are you there? You're not. And then if it's there, it communicates, and it's not. It goes the other way. It's useful for live video and audio transmission over the internet. Also more effective when carrying messages that fit within one data packet. So small data sets and things like that. So a UDP area contains only 4 fields: the source, the destination, the length, and the checksum. So it's sending it out. So that's UDP. So you can see how a UDP package is a lot more smaller than when we saw the TCP/IP. A lot more going on, a lot more things happening right here, and it's a lot more stuff that's going on with TCP/IP. But with UDP, very simple. Let's get in, let's get out. Are you working or are you not? So let's talk about the internet protocol, the IP. It operates on the network level of the OSI model. It tells when the data should be delivered and identifies data sources and the destination and the address. So the IP part of the TCP/IP protocol transfers more than one LAN segment and more than one type of network through a router. So basically, what it's saying right here is that it can go once it hit one router, it's just not gonna stop at that one router because it might be 3 or 4 hops or 5 or 6 hops to get to its final destination. So this IP protocol is going to go through more than one LAN or a router to get to its final destination. So this is also unreliable in connectionist. It means the IP does not guarantee the delivery of the data or transmission can be established. It's going to go out there and try, but I'm not guaranteeing anything. Okay, it depends on TCP to ensure that the message and the package get put back together in its rightful order. And as you guys read the book, it's going to explain a lot of that. as you read, and then it's like the IP header as it's going across here, and it's it's doing the checksum and this thing's right here. So we'll just move on from there. Now IPv6 is another protocol. We talked about IPv4, the whole network, and everybody's going to IPv6. Um, in my experience, in my 15, 20 years in this industry, I've never had to deal with a lot of IPv6 troubleshooting. Um, it's kind of like, I guess maybe because my career kind of took me out of that arena. It's widely used right now, but I have not had to. I don't have a lot of real world first experience on it because I kind of moved away from that type of segment. Accommodates for much longer IPv6 addresses. There is no fragment offset field. IPv6 hosts adjust their packet size to fit the requirements of the network before the IPv6 sends a message. So it's doing a lot more here. They came up with IPv6 because IPv4 was, they felt that we were kind of running out of IP addresses and better network packets and things of that nature. So this is supposed to be a lot better, a lot faster, a lot more reliable. But like I said, I haven't had no real world experience on it right now. It's kind of hard. And I think what I'm gonna do tomorrow at the job is just kind of peruse around in the data center and just kind of see what things we have on IPv6, just to see if I can find some more what's going on out there with IPv6. So Internet Control Message Protocol is a network layer core protocol that reports on the source or failure of the data. ICMP, it can indicate when part of a network is congested, when data fails to reach that part of the network, or when data has been discarded by the TTL has expired. So it took too much time. So that's what's happening when you're dealing with this. ICMP also announces the transmission speed, transmission failure to the center, but it doesn't connect it. It's gonna let you know that, hey, I didn't get it. I'm not fixing it. I just didn't get it. So that's kind of what ICMP does as well. So so when you go through the book this read and you read through it, also go over the glossary in the back of the book just so you can kind of understand some of this terminology as well. So let me do something real quick. I need to pause the recording. So also with ICMP, tongue twister, you guys get used to saying that. Okay. This is how it's breaking down the packets. It's 8 bits in length. The code is 8 bits. The checksum is 16 bits, and rest of the header is 32 bits. So that's just it just gives you kind of a packet breakdown of how it works. Address resolution protocol. This is one that you will hear a lot in networking, and this is something that you should get familiar with. They call it ARP. Works in conjunction with IPv4. And it discovers the MAC address of the host or the node on the local network, and it maintains a database that maps all the IP addresses to the MAC address. You remember we said earlier in the chapter that every computer network card has a MAC address. It has its own physical address to that, and so what the ARP table does, it maps. It creates a table and it maps all those IP addresses to the physical network card MAC address. Okay, ARP works at layer 2, and that uses IP in layer 3. ARP is a layer 2 protocol that uses IP in the layer 3 on the OSI model. It operates only within the local network. Okay, ARP relies on broadcasting, and you can see the ARP table. I think we're going to show. So this is a sample of an ARP table. ARP table. You have your IP addresses, and this is the MAC address here of the network card. And the dynamic DHCP, and then you have a static. This is a locked-in hard address here. So this is kind of an example of what you see here. So if you were to use this command, if you go to a Windows DOS prompt, just go to a command prompt on any computer, and you type ARP space minus A, if your computer's on the network, you should see an ARP table, something similar to this, of all the systems that it has here. Let's see here. Let me just see if I can do it. I don't even know if I have anything on my network here at home, but okay, I have a few things out there. So basically, this is everything in my house that's kind of wireless that's on right now. You know, this is probably our router right here. Looking at these IP addresses, and then these are probably some just, I don't even know what devices they are, but these are some of the devices. But that's my personal network here for right now. Ethernet, most important data link layer standard, capable of running on a variety of different networks, offers excellent throughput as a reasonable cost. Most popular network technology used on the most LANs. You know, everybody know about Ethernet networks. We've been talking about them all semester. So adds both the header and the thread to the payloads. Okay, so this is kind of like how the Ethernet frames work. And this is, and when they talk about this, we're just talking about how the data is broken down, the packets are broken down as it's sending it across the network there. The header or the FCS makes up to 18 bytes of frame around the data. Data portion of the Ethernet frame may contain up to 46 to 1500 bytes. So it's talking about this little area right here, okay, as it's coming through the frame. The MTU, maximum transmission unit, the largest size of the router, in a message path will allow at the network network layer. Okay, so this is kind of how Ethernet works here. So special purposes networks use a proprietary version of Ethernet which allows for jumbo frames. So if certain things are, you know, they can that can be adjusted, and that's something that some network administrators may alter. Okay, a router joins two or more networks together and passes packets from one network to another. You guys are pretty much familiar with how routers and how they work, so we're not going to spend a lot of time on this. But we just keep in mind that routers can do the following. They're, you know, connect dissimilar networks. So, you know, if you have a LAN to a WAN, that's why I say dissimilar networks, because, you know, LAN is a local area and a WAN is something really, really large. And routers connect those two together. Interprets, you know, layers 3 and often layer 4 addressing determines the best path for the data to travel. So these are a few different type of routers. Internet service provider in business, and you know, you got your personal routers here. You guys have probably seen these before. If you haven't, these are what you see in big data centers and things of that nature. Routers may perform any type of the following operations. It can filter broadcast transmission, prevent certain types of traffic from getting back to the network, and support simultaneous local and remote connectivity. Routers are very, very important. Monitor network traffic and things of that nature. So every network has a router. There's different areas that routers will work on the network. Some routers, core routers, get called the interior routers. They talk about these guys here. And as you say, this is just nothing but a network. The whole network, and routers almost like a traffic light. You know, systems is going across the network. You got routers on the edge of a network. You got the core routers inside of a network. And then once you get out, you got the exteriors here. You got the internet service provider over here sending routers. And that's just kind of how they work. And you guys read more about it during the week. Multi-layer switches. They work on, you know, layer 3 and 4, capable of interpreting a layer 3 data and works much like a router. Usually faster and less expensive. Primary difference is the way that it is built. Okay. Layer 4 switch capable of interpreting layer 4 data, also known as content or application switches, enable switch to perform advanced filtering, keeps statistics, and provide security functions. So they're a little bit more secure, a lot more secure than routers, but they're like traffic lights. They still kind of do the same functionality, just a little bit smarter. They do have routing tables. Oh, I'm sorry. Routing tables are a database that maintain information about the host and the network. So, you know, you already have routing tables, and I don't think the book gave an example of that. Routing table on routing tables, they do rely on um, routers rely on them to identify which router is the next hop to reach a particular destination. So that's what the routing tables do. So when you do a trace certain, you want to see how many hops it is to a certain thing. It's also talking about through the routing table here. So so if you have a routing table here, so a routing table, you have your internet here, you have a computer here, and a switch here. The routing table is what's going to tell this computer go to this switch router. Do I go to if I'm trying to get to this computer here, or say this network printer here, go to the switch router, and okay, do I go to this one? No, that's not the right one. This routing it's gonna probably tell me to go here, then here. So that's what the routing table do. It's like a traffic light. It's going to tell you which way to go. Routing path types, you got the static path. Network administrator configures a routing table to direct messages along the path. You know, so you just like a static path route between the small business and an internet service provider, and then you got the dynamic routing, automatically calculate the best path for two networks to maintain the information on the routing table. So it just depends on how you can get very very creative when making your network and making it fast as well. We I was on the call today, and one of our guys on the call was concerned that the server was in Arizona, and he was wondering about data latency and data transmission. And I was like, it doesn't matter. I said, because the application's here, and I was just telling them how fast. So if this happened at the blink of an eye, you wouldn't see it. It wouldn't be a difference whether it was in California or the servers in Arizona. The router commands allow you to view the host of the routing table. So on a Linux server or Unix, you use the command route. On a Windows, basically you route print, and then on Cisco devices, show IP route, and then that will allow you to view the host routing table. I don't think I have a routing table here, but let's see. Uh, Just a little bit here. Let's see what we got here. So if I type in route print for a Windows-based PC, this is what you'll see. So active routes here. So these are the links to the gateway interface and the metrics here, and then active routes is metric network destination in the gateway. So basically, this is kind of what you're seeing on the routing table and you can use the same command on your own PCs themselves. Okay. So and if you was on a Linux system, you just type route, or if you was on a Cisco system, you use show IP route. Okay. So the metrics properties of the route by the router determine the best path to destination, how many hops it takes, the bandwidth, the delay, the latency, the load, the traffic, maximum transmission for each package. So these are just some of the things that the routing matrix will do. Okay. Routing protocol used by the router to communicate with each other to determine the best path. Router rates the reliability and the priority of routing protocol data based on these criteria, the administrative distance, convenience time, overhead, so it just looking at a few things here. So these are some of the commands that you will see when using routing there. So this is the interior exterior gateway protocol. So when on the slide, I think it was up here, it was talking about the exterior and the interior gateway, the protocol. So, when you have them, they have different things that they're good for, they're known for. It's designed for the use of the core routers, only for the core routers, not handcuffed by the internet the IPv4. So it's easy to adapt to IPv6. Service providers generally prefer IS-IS because it's more scalable than OSPF. So, like I said, it gets a little granular here, and we're not going to rely a whole lot on this because you guys probably will never ever see this. let's see here. Now, troubleshooting. Troubleshooting, like I said at the beginning of the chapter here, it's always in every chapter, especially going forward, pay particular information, attention to the troubleshooting portion, because although we talked about the theory and what's going to happen is this is happening at the flash of a blink of an eye. You're never going to see this. So sometimes you just got to just think about what happens. It's really going to help you with your troubleshooting piece. Okay, so TCP/IP comes with a set of utility that can help you with that. And you're going to get some of these commands like net stat, so if you, I'm going to make this a little lower here, but if you just like when you're troubleshooting, and if you just type in some of these commands, it's just like, did it not display it? Okay, hold on for a second. Oh, trying to get this up here. So there you go, net statistics. So here you go. So it's pulling them up right now on my network here. Close, wait, establish. So there's a whole list of commands that you're going to be able to see here. Information that can be obtained from NetStat includes the port in which the TCP/IP is running on. So let's see if we can find the port here. And I'm assuming this port. These are the ports right here. These are the ports here. Okay. Let's see what this says here. Which network connections are currently established for the client? So these are, you see my name here, Dirk Smith. These are the established network connections. Okay, it's the same. I'm not exactly sure what's the different IP here, but these are the established network connections here for me. How many messages have been handled by network interface with was active? How many messages do we get here? Foreign addresses established, close, wait. Close, wait. Time to evaluate. I'm not exactly sure which one are the messages here. Unless it's just talking about the state here. These are just the state of the messages there. And how many errors? Did we get any errors? I ain't see any errors. So that's good there. So anyway, that's kind of what that command does. Trace cert. So trace cert utility uses error messaging from router to the map node. Okay, so it's going from here to the destination. But I was just showing it, so that's the reason why we didn't see any messages. But it was just kind of displaying what. So trace route continue. So this. Oh, that's what I'm copying. Anyway, I just type it in. I think you have to put in like an IP address that you're going to trace to. Yeah, I'm not doing it right. Let's see. I think you have to put IP trace rate time limit. Trace test might stop before reaching its destination. The reason device can trace the attempted to reach down. It's too busy to process lower priority messages, so the UDP IMCP does not accept UDP ICMP transmissions. Firewall about tracer cannot be detected route. Oh, you know what? I think I got to put tracer. Did I do tracer last time? What did I do last time? Let me see something. What was this? 1 second here. NetStat trace route. This is a Windows-based computer. That's why. TRAC 42. There we go. So just type in. If you type in just trace cert here, and then when you just type in the command here, this will tell you all the wildcards you need for that command. So space -D, it resolves IP address to host names. Okay, minus trace cert -H. how many maximum hops to get to its target destination. So, and then this timeout and the wait. So, an IPv6. So if I just go like this, space minus D, it should resolve. I may need to put IP address in. I think I need an IP address. Well, I don't know if it's gonna work. It's not really set up to work here. I need to be on like a more of a private network here. But if I go like, let's see, if I go -H, then if I say Google, bad -H. Oh, G O. Oh, wait. Yeah, it's supposed to be like, it's supposed to, oh, what is it? No. I'm trying to remember how it worked. I think you have to put the, it's supposed to be like this. I'm not sure why it's not working. -H. Oh, yeah, put space -H. Oh, 2 H's. Come on. Oh, yeah, I'm not exactly sure why it's not working. But anyway, you're supposed to be able, and we may have to play around in the lab, but that's kind of what these commands will do here. So if you go to, here you go, ping path -n google.com. So that should be the same as instruction of IP is its host name. So let's try this path ping. Let's see. Path -n. Yeah, that one worked. Why trace search didn't work? Interesting. So it's telling you how many hops it's taken to get to trace search. So it's how many hops. Computer says it for 75 seconds. Just interesting. Oh, I'm just kind of curious why this one. Windows, ERC utility. Anyway, I don't know. I can play this forever. All right. So anyway, and the other thing, TC dump is a free command that links packet sniffers that runs on Linux servers and OS. You must either use the sudo command or log on to the root cause of the TC dump. It captures traffic across the computer and network and things of that. So this is like for a Linux command, TC dump. So some of these commands are pretty good. This is still talking about Linux. This is kind of what it does for Linux files if you guys are a Linux user. Okay. These are all Windows-based command line utilities. ART, we talked about ART, dig, ipconfig, ifconfig. You guys we've seen that netstat, we talked about the statistics, nslookup. You guys can, so these are different commands, ppath. So these are, well, there's some Linux here too, but these are also Windows commands as well. So you're going to see these over the course of your careers, or just as you set stuff up at home, or even at your job if you guys work in computers. So over time, you guys, when it start coming around, you guys just start remembering how they work and things of that nature. Okay. Duplicate MAC address, two devices on the same network with the same MAC address is a problem. It's definitely. So if you have, I've never seen a duplicate MAC address, but what I have seen is a duplicate IP address. Now, unless they're typing the MAC address in wrong and that's hexadecimal, that's very hard to do. I've never seen that. But I have seen duplicate IP addresses, and these networks are so smart that as soon as the network sees it, you don't even have to program it. As soon as it sees the duplicate IP address, it's definitely going to throw an error and let you know it's going to say, I detected a duplicate IP address on the network. So I've never seen a duplicate MAC address. Solving common routing problem, hardware failure with routers and switches and NIC cards and other hardware go down. You can use trace cert and trace route. And what that does is that when you type those commands in, it tells you how many hops. And then if you know your network well, wherever the hop stops at that particular router, then that's probably where the break in the chain is. And that's what it's doing. Okay, ping to test the network connectivity, and you guys all use the ping command. You just put that in, it's just going to send out 4 packets, and it's going to actually come back with a reply. Okay. Discovering neighboring devices, a process used by router to learn about all the devices on this network. On the IPv4 network, neighboring discovery is managed by the ARC table, and you get help from the ICMP, and the IPv6 device uses network discovery protocol to automatically detect the neighboring devices and automatically adjust the neighboring nodes fail or they need to be removed. So, and that is chapter 4. So I'll go ahead and post this. Stop the